Recap kind of the ideas that we talked about with respect to exponential growth and decay models, which is what we're going to look at today, and especially in these times since we're experiencing a contagious disease that's spreading, and they tend to do so with exponential growth or decay. So what we're going to do is we're just going to kind of start by reviewing a little bit what we mean by exponential functions and look at how they kind of behave. And so you could look at this situation here. You know, if I had 3 bacteria and they double every minute, you know, could we describe what's, you know, the amount of bacteria look like over time? And so what we're going to do is we're going to, you know, create a table of values that shows the number of bacteria at a given time in minutes, and kind of look at a relationship that exists here, a functional relationship, and then we're going to sketch our data and describe what we see. So looking at our table, this is something that I want you to notice here. We're often going to be using t-charts to represent our data, but you'll notice that the time is listed as in minutes, and then we have a number of bacteria. Usually we'll represent these as x and y, where x is our time and y is our amount at a given time. And one particular time that I really want to point out here is time 0, which is kind of a curious amount. Graphically, this is going to be our y-intercept, but you know, in a tabular format, we kind of interpret this as our initial amount at this time. So at time 0 is right when we started. Let's say I had 3 bacteria here. So you know what's happening every minute is that these are doubling. You can see that, you know, this is meaning that I'm going to take it by 3 and multiply by 2. I'll get a 6 here. Take that times a 2, and I would get a 12 here. I take that times a 2, and you can see that this pattern just kind of carries on. And you can also see that even if we had a small, we call this a little seed right here, it can grow quite large over time with this exponential growth, because, man, if you're doubling everything every time, it kind of doesn't take a long time for that to get very, very large in size. So you're going to notice that at the 5th minute, we would have 96 bacteria if you started with a small seed of 3, and it's doubling every time. So how about the 10th minute here? Now, this is interesting because you'll notice the pattern is times 2. This would mean that I'm going to have to take 96, and since I'm at the 5th minute, I'm going to have to multiply by 2 5 more times. So really what we're going to try to focus on here is maybe writing a rule that models or a model that represents the number of bacteria n at any given time t. And the way this kind of works is, if you look at this table right here, if I wanted to say find my bacteria at the 1st hour, I had to take my initial amount times 2 because I'm doubling it 1 time. But if I wanted to find the 2nd hour, that was 3 times 2 times 2, or in other words 3 times 2 squared. Really because I'm starting with 3 and I'm going to double it 2 times to get to this amount here, and then you can start to see this pattern picks up 3 times 2 to the 3rd, 3 times 2 to the 4th, 3 times 2 to the 5th. So one might infer that to get this value here, it's going to really kind of be interpreted this way. I started with 3 of something, and what I'm doing is that I'm taking it times 2, and in this case, because 10 minutes have passed, I'm going to have to double it 10 times. And so we really say 2 to the power of an amount of time, or times that we want to compound here. So 3 times 2 to the 10th, 3 times 2 to the 20th, and generally speaking, we would say the number of bacteria we have here, let's see if I can write on this really quickly here. The number of bacteria we have is equal to the 3 we started with, and it is doubling every time given a factor of time here, or an amount of time. We'll put that as t because that's what I wanted as my time. So this would be my model here. We could also write this as 3 times 2 to the x, and we kind of just look at this as at a given time x, what's the amount of things we have if we started with 3. So this is our initial amount, and this is our growth, and it could be or a decay, right? But our growth factor, the thing we're multiplying by every time. So looking back up here, you know, I wanted to get some values here. We could take a look at this generally speaking. I always say 3 times 2 to the power of 10. We get, yikes, 3072. So after 10 minutes, you have 3072 on your arm. And then, let's see, after 20 minutes, just to gross you out here, we started with 3 of something, and we multiply it by 2 to the power of 20. Oh man, you have 3145728. 3145728. So we get this right here, and just after 20 minutes. So this is some growth here. And in terms of what we're going to do a lot of the time also is just represent this with a graph. And so graphically speaking, we would see something that started, you know, let's look at just the first 5 minutes here. You know, 1, 2, 3, 4, 5. Started at time 0, went out 5 minutes. And in terms of our y scale, I mean, this goes up to 96. We'll call this 100. So this would be about, what, 50 right here. And, you know, maybe like this is like 10. So we started with 3 of something, and that 3 became 6, and that 6 became 12, and that 12 became 24, and that 24 became 48, and that 48 became 96. And so we start to see something that looks like this, and it's very, very much continuous. So you'll recognize that this is what we were referring to in the previous chapter 3 as exponential growth in this case. And so a curve that is growing at a constant rate, but its rate of change is changing. Actually, its rate is increasing as we go left to right here. So it's getting steeper and steeper and steeper and steeper. So speeding up, okay? And this is what we mean by exponential growth. So, you know, when we look at exponential growth models, we're going to be looking at things like this. I'll point out on the next page here. But we'll say that you're always having some initial amount, and it is growing or decaying by a factor of b over this amount of time. And this is kind of how we look at these models here. So this is our general model, y equals ab to the x. Some recap here. Our graph tends to, if its growth gets steeper and steeper as we go left to right, but it does go left and right forever and ever. And so its domain is negative to positive infinity. And it only hits positive values for b values greater than 0, but opens upward above this, the x-axis here. We would say that a represents our initial value, our initial amount at time t. This could be shown to always be the case. If y equals ab to the x and you throw in 0, then we would get a times b to the 0, or a times 1, or just the initial amount. So it's important to know that if we represent these graphically, our initial amounts always are y-intercept. And another fact is that it never quite reaches an amount of 0, okay? So it always approaches this x-axis and has an asymptote of y equals 0 here. So A represents our initial amount for our model. B then is our growth or decay factor, where y represents the amount of our initial amount that's left over at a given time x. And this is how we kind of generally speak about exponential functions. Well, there's a pretty slick form of this, and this is our continuous growth or decay model. But we say that we write it a little bit differently here. A equals PE to the RT. And we use this whenever we talk about continuous growth or decay. So I'm also gonna write this as y equals AE to the RX. But we're still going to be looking at x as representative of our time, okay, and y is representative of is an amount of something at a given time. So A is our amount of something at a given time t, where p is our a value formally, and is our principal or our initial amount, and then E is Euler's number, so just this constant 2.718, and then r is our rate. Here, we write this as a decimal, but this is a really convenient model, and the reason why is just because we would only need to model it using two things. Do we have what we started with, the initial amount, the seed, and do we have the rate of growth or decay? And it's worth mentioning with respect to growth or decay, if it's growth, that's going to mean your rate was positive. If it's decay, it's going to mean your rate is negative, okay? So we're going to be looking at exponential growth and decay modeling. Can we write a model given some data points here that would help us predict, say, an amount of bacteria at a given time, or the amount of time needs to pass for there to be a certain number of bacteria present? And so that's what we're going to do with this slide here. And so I hate to be so morbid about it, but we're looking at some COVID-19 data. And this is data that I've gotten from the CDC, their website, but essentially you can see all the way up to April 1st, Wednesday, I need to fill in that data there, but March 31st we had 186,101 people infected, and it started on January 22nd with 1 person infected in the United States. So this is pretty crazy growth, and you can see that this is really modeling exponential growth over time. So maybe our idea would be, like, could we potentially write a model to model this data over time? And if you're going to do so, like, which data points would we want to use here? And so I would say, first of all, and I can pop over also, I've got this in Desmos, but the first data point we want to start with is always just our initial datum. And that would be at time 0, if we have it, how many people were infected. So this goes back to, in terms of writing this model, we need our initial amount. Our initial amount in this COVID-19 case is going to be 1. And then we're also going to need the rate, which is, you're going to see, is not available to us here. Okay, I can't determine the rate just by looking at this. So what we'll do is we'll grab another data point out here. Maybe, I could grab this one right here, I could grab this one right here, or I could grab the most recent one that I had at the time when I made this, which was the 61st day, that there were 44,183 people. I think that the one I'm going to use for the sake of this example is at the 60th day, because it's a nice round number. There were 33,404 people. So let's take a look at a situation where maybe I wouldn't give you the data, but I would just kind of hook you up with the situation here. So let's read. Consider the spread of COVID-19 in the USA. On January 22nd, okay, there was the first reported case. So on March 22nd, the 60th day, there were 33,404 reported cases. What we want to do is write a continuous growth model to represent the number of infected people. To represent the number of infected people in the country at a given time of day. So a couple things, just good habits to have whenever you deal with problems like this. I'm going to write X and Y, but you can write T and then A to represent our time and amount. Two good things. Always fill out a T-chart and always just kind of make a rough sketch of your graph here where this is time and this is the amount infected at a given time. So what do we know? Well, at least with respect to our model, we know that we started with, at time 0, 1 person infected, and that was on January 22nd. And then 60 days later, on March 22nd, okay, 33,404 reported cases. So, we would say 60 days. You could call this arbitrarily 60 right here, but the idea would be we'd throw a point way up here, of course not really drawn to scale here, but we would say that I have an exponential curve that's passing through this like that, okay? And what I want to do is I want to come up with an equation or a model for it so I can start to make some predictions where I know that I start with one case and I know that after 60 days I have 33,404. So what we're going to look at doing is writing a model here. Let's put in our data, 60, 33,404. So just with the idea of what's going on here, we want to write a model for this. Remember that our model has the form A equals PE to the RT, or y equals AE to the RX. What we're going to be doing is writing our model where we plug in our initial amount and our rate. Now, in terms of do we know the initial amount? We do know the initial amount in this case, but we do not know the rate. So with respect to our model, at least our incomplete model form of this, we would have our model as the amount is given as 1 e to the rate time. We just don't know the rate. So because we have this extra data point, this is what we're going to do. We're going to plug this in. We're going to plug in 33,404 for our amount. And we could say that we know it was this amount if we started with one person and it was e to the rate times 60 days. Because at the 60th day, that's when we had this amount. So what we're going to do is we're going to work on solving for r, and what that does is it means that we have to involve some solving for exponents or exponential equations. Remember that with an exponential equation, our job is going to be to isolate this exponential base here and undo it with its inverse, which is a logarithm. So really quickly, let's review this property of logs and exponential things. If you take the log base b of an exponential thing base b, and they have the same basis, then this logarithmic thing and exponential thing kind of cancel, and you get left with the argument here, which is just this x right there, okay? So that would mean that if I want to undo e to the x power, I would have to do log base e of e to the x power, and those would cancel and I would get x. One thing I just want to mention is that remember that log base e is the same thing as the ln. So really we're going to see this property show up here, and just get used to it. When we're solving with continuous growth models, we always have base e. And so we have to use natural logs to undo it and get to our exponents here. So here's the idea. Let's get e by itself. That means we're going to divide both sides by 1, which you're going to think is absurd, but in this case, like is the thing we do, generally speaking, is divide out your initial amount. We get e to the, and I'm going to write this as 60r. At this point, I'm going to take the ln of both sides. So ln of 33,404 is equal to the ln of e to the 60r. And here's where we get this cancellation right here. So our ln of 33,404 now all of a sudden just equals 60r. And this is the part where if we divide out our time, which is 60, we're going to get left with our rate, which is kind of nice. We'll say our rate is equal to exactly ln of 33,404 all over 60. And this is where we're going to need our calculator. So we'll say that, turn this on, 33,404 divided by 60. We get 0.1736, so about 0.1736. I'm going to put a box around this, and again, call this R. But the important thing here is that, and I'll scroll back up, we needed two things. We needed the initial amount, we needed the rate. So I'm going to go ahead and write both of these things down. We say our rate is about 0.1736, about a 17.36% rate, and our principal amount is a 1. So with respect to our model, we've got this, guys. We started with 1 of something, and it was growing at a 17.36% rate over time. So this is what I want you guys to be able to write, given data that grows exponentially like this, saying, hey, if I know where it started, we'll call that what I had at time 0. We'll pick a different data point and solve for a rate. But once I've got that, I've got my model. Okay, so what are we going to do? Well, we're going to use this model to do all sorts of stuff like, hey, use your model to predict the number of people who are going to be infected on the 65th day, so like 5 days later. So the way this works is, and we can put this in our table over here, we're just going to use our model. We would get 1 e to the 0.1736 times 65. I should put this in a different color here. In parentheses, 65. Well, 6 is kind of like 5s. And then we can just evaluate for this. And so, getting my calculator here, we would say, hey, start with 1. We'll hit second ln to get our e out here, and we'll say it was a 17.36% rate, so 0.1736 times 65, enter. And so we have about 79,538, 79,538, and I normally go out decimal places here, but I'm going to be lazy. I'm going to say about 80,000 people on the 65th day. And so, how good does this model actually do? I mean, we see this data here. Let's do some things. First of all, let's graph y equals 1 e to the power of 0.1736 x. So you can see that our model here, it kind of goes through the data pretty well. It misses a lot of data points on the underside here, and then it misses them on the upper side here. But on the 65th day, I didn't have a data point for the 65th day here. I went all the way out to the 61st. So let's see how we did. I've actually got the COVID-19 data. So the 65th day is right here. And on the 65th day, there were about 103.3 thousand reported infected. And this is predicting, okay, only about 80,000. Okay, so pretty scary. So how about this? How about on the 70th day here? And I think I've got this wrong. It should be the 70th day here. So 5 days from then. And so if we put in 70, again, we could go find this value right here. I'll tell you what. One thing I want to do is use our calculator to actually go make a table for this data, which is something I'm going to actually ask you to do on part E of this problem anyways, and now's a good time to do it. Instead of typing this in, and it's really easy for me to do, I can hit second enter and go back and change my 65 to a 70, and I say, here it is. Okay, I actually need to be able to do it this way. But let's do this. Let's hit y equals, and what we'll do is we'll go put in this model. 1 e to the power of 0.1736 x in parenthesis, and instead of hitting graph, behind graph it says table, and by hitting table, mine defaults to starting at time 0, and we had 1 here, but you can see as time's going on, okay, day by day, you can see how this is, the model is saying it's growing over time. One thing I want to do is on part E, it says use your graphing utility to create a table of values based on the model. And it says use intervals of 5 years. So behind where it says window up here, it says table set. We can hit second window, and where it says table start, we'll start at 0. And where it says delta table or triangle table here, we're going to change that to a 5. So that when I hit second graph now, and I go to my table, I can see this changing over time. So we wanted to explore the 70th day. Let me scroll down here. The 70th day predicted on this model is 189,473. 189,473. Okay. And it's really convenient to be able to use your calculator to tell you this. So, we would put these two values in right here and here. Okay. So part D, it asks this question. It says, hey, during which interval, the 60th to the 65th or the 65th to the 70th, did the amount of infected people change more drastically, and why does this happen? Okay. So you'll see from the 60th to the 65th here, get our calculator out. Quit. Clear. On the 65th, we had 79,538. Try again. 538. Minus on the 60th day, we had 33404. So in that 5-day interval, it changed by this many thousands of people, 46.1 thousand. Between the 70th and the 65th, so we say 473 minus the 79538. This is how many it's changing by. So definitely between the 65th and 70th day, and to kind of answer why this happens is because, I could go out further right on my curve here. Let's see if I can buy myself some more space. Imagine that we don't put this here, okay? We say that this is the 65th day. We'll put 60th here, and then the 70th here. For a given amount of time, okay, so 5 years, you're going to get some good growth here on your curve, okay, between those two amounts there and there. But when you go the same amount of time, your y values are getting steeper and steeper the further right you go on this curve. So you are covering way more ground on your y-axis than you are on the left as you go out to the right. So we see that exponential growth curves, why does this happen? Because they're growing steeper and steeper and steeper and steeper. Okay. So for the last part of this, F and G here, let's take a look at those. We want to do a couple things. So F, it says use your model to calculate the number of days that it's going to take for there to be 1 million infected people here. And so this is a little bit backwards. Last time I gave you some times to plug in into your model and go find amounts. This time, and maybe I need to switch my color here. We'll go over a nice contrast color here. What we're asking is what's the amount of time I have to wait for 1 with 6 zeros to be the case. And so we're going to use the same model, except for instead of plugging in for time, we're going to plug in for the amount. 1 with 6 zeros. When I have 1 million infected people and I start with one person who's infected and our rate is 1736, and this is times t. Let's go solve for our time, and this still involves kind of the same process. So we'll divide both sides by 1. In this case, you know, we certainly get 1 million. And that's equal to e to the 0.1736t. Now here's where we take the natural log of both sides. And if I take the natural log of this e on the right, it's going to cancel out. It's going to leave behind a 0.1736t. And then we're going to take our natural log of 1 with 6 zeros and divide it by our rate, and that should leave us the time. Okay, and so let's get a value on this. How many days until 1 million? It's kind of not fun to calculate. So not quite 80, according to the model. 79.6 days. According to this model. And you can see this with your table also if you hit second graph. You can see it clicks over to 1 million here. This is 1.08 E6, which is really 1.08 times 10 to the 6th power, so scientific notation. So the last part of this is the other not fun part about this, but what's the doubling time of COVID-19, assuming the data values that we've used here? So it says use your model to determine the amount of time it takes for the number of infected people to double. Well, what makes this a little bit different is our model looks like this at the moment, e to the 0.1736. So what we're going to say is, well, doubling time, if I want to find the time when this is double, then I have to say, well, then this amount here, a, would be equal to twice of what I started with. So what we're going to do is we're just going to put in double the amount of the initial amount here, and we're going to work backwards for the time for this to be the case. And so using the same steps as we tend to do, we'll divide by 1. We'll take the ln of both sides. So 2 divided by 1 is 2. Take the ln of that, and then we'll leave behind 0.1736t. And if we were to divide that natural log of 2 by 0.1736, that would give us our time to double. Let's take a look. We would get the ln of 2 divided by 0.1736, almost 4 days. So about 3.99 days to double. So it's doubling about every 4 days, which is also a scary thought in and of itself. So that's what I wanted to kind of review a little bit with you guys today, how to write this model. Remember that you need 2 things, the initial amount and the rate. And then you can write your model, and then use your model. And not to bum anybody out with this exponential growth, but I just want to give you a heads up that it's more of a logistic growth curve over time. And so that is to say that there is a peak on the population here. There's no more than this many people. And so, you know, you get this exponential growth over time, but there's going to be a point at which it kind of goes from concave up to concave down. We give this point a name, a point of inflection here. But because you run out of people to infect, and so it would slow down the rate of infection, which will be a good day when we see that. So use this to kind of help you go through that exponential worksheet A and take a look at how you can write some models and use them. Cheers.